how do you describe the fluid, effortless motion of a coasting skater? A simple answer to that question is that a coasting skater moves at a constant velocity. The term velocity is new, and I'm about to define it. In fact, in a short time, I'll restate Newton's first law using better, more sophisticated language. But in order to do that, I need to introduce 3 physical quantities associated with motion. Those physical quantities are position, velocity, and force. Position is the measure of an object's location in space. For example, my position is about 6.5 feet or 2 meters in front of this jar. You'll notice I needed 3 things. First, there's the reference point from which to work with, this jar. Second, there's my distance from that jar, about 6.5 feet or 2 meters. And finally, there's the direction from that reference point to me, namely in front of. If you leave out any one of those 3 aspects of position, the reference point, the distance, and the direction from that reference point to the location you have in mind, you don't know the object's position. To show you that, let me change my position. Well, first off, if we lose that bottle, and I say I'm 6 feet in front of, we don't know, you don't know where I am anymore. Okay, we need the bottle, the reference point. Okay, so now suppose you know that I'm in front of the reference point, but you don't know how far. You lose the distance part. I could be here. I could be here. It's a problem. And finally, suppose you forget to mention the direction from the reference point to me. Well, I could be 6.5 feet, that is 2 meters, from the reference point here, also here, also here. So the direction matters as well. You need all 3. Position is a distance and a direction from a reference point. Physical quantities like position that have both an amount and a direction are known as vector quantities. You're probably familiar with physical quantities that have just an amount, like the temperature of this room, or the duration of a concert, or the size of your computer screen. But there are also many important physical quantities that have both an amount and a direction. They're vector quantities. And if you leave out the direction part of a vector quantity, you haven't specified the whole thing. We measure position in units of distance. Physicists normally use the SI, or System International units, and the SI unit of distance is the meter. That's about a meter right there. Well, because most people in the United States are relatively unfamiliar with the SI units, the meter in particular, and because this class is all about familiar things, I'll also use more familiar units. In this case, more familiar units of distance include the foot and the mile. When an object is moving, it has a velocity that's not 0. Velocity measures the rate at which an object's position is changing with time. Velocity is another vector quantity. It has an amount and a direction. The amount of your velocity is the speed at which you're traveling, and the direction of your velocity is the direction in which you're heading. Let me show you my velocity. Right now, my velocity is 0, but I'm about to develop a velocity to your left. Here we go. I'm now moving toward the left, and my velocity is, maybe half a foot per second to the left. That's different from this velocity. Now, I'm moving about half a foot per second toward your right. That's a different velocity, even though my speed is the same. As you can see, velocity has an amount, my speed in this case, and a direction, the direction in which I'm heading. And if you don't specify both of them in specifying my velocity, for example, you've left out some important information. You haven't fully specified my velocity. We measure velocity in units of distance per time. The SI unit of velocity is the meter per second. In the United States, more familiar units of velocity are feet per second and miles per hour. I have one more physical quantity to introduce: force. Force is the physics term for a push or a pull, and it's another vector quantity. For example, if I push on this book, I'm exerting a force on it, and that force has both an amount, which is how hard I'm pushing, and a direction, which in this case is away from you. The SI unit of force is the Newton. 1 Newton is about the force that a small apple exerts on your hand when you hold it. This is actually not a small apple. This is about a 3 Newton apple. A more familiar unit in the United States for force, the pound, or more specifically, the pound force. 1 pound force is roughly equal to 4.5 newtons. We can now redraft Newton's first law of motion using better language. To start with, we can replace the vague term influences with the more specific term forces, so that Newton's first law of motion becomes an object that is free of forces, moves in a straight line, and covers equal distances in equal times. But we can also redraft the second half of that law. An object that is traveling in a straight line is always heading in the same direction, constant direction. And an object that is covering equal distances in equal times is always traveling at the same speed, constant speed. An object that has both constant direction and constant speed has constant velocity. So Newton's first law of motion, in its final form, is that an object that is free of external forces moves at a constant velocity. A skater who is experiencing 0 force is covered by Newton's first law of motion and will move at constant velocity. The skater is coasting. Avoiding any external force is difficult or even impossible. But it's relatively easy to have the individual external forces on a skater cancel one another, so that the skater experiences no overall external force. For example, if you push a skater to the right and I push that same skater to the left equally hard, our 2 forces on the skater cancel one another, and they have no overall effect on the skater. If all of the external forces acting on a skater cancel one another in this way, the skater has no overall external force acting on her, and she obeys Newton's first law of motion. She's inertial, and she travels at constant velocity.